Hello, everyone. I'm very glad to be here to present my current work, which is a current generation approach for the electric autonomous diorite problem. And I'm USG from St. Petersburg, and this work is collaborated with Professor Sophie Pak in Linz University, and also with my supervisor Jacob and co-supervisor Nicola. And in my presentation, I will tackle the electric autonomous diorite problem, which I will explain to you later. And we have proposed an optimization approach with this current generation approach to tackle this problem. And before that, I will tell you a small story to explain what is diorite problem. This story is based on 4 of my favorite characters in Hunter x Hunter: Killua, Gon, Kurapika, and Leo. And they have passed 3 transportation requests via the platform of Hunter Association, where are shown in the table. So Killua and Gon, they want to be picked up at the origin Kukulu Mountain and be dropped off at the Sky Arena, and they are expected to be picked up during this time window, 8:30 to 9:30, and they want to be dropped off between 11 o'clock and 11:30. And Kurapika, he has a mission to fulfill at New York. So he proposed, so he has passed a transportation request that he wants to go travel from Tokyo to New York, and here is his expected time window for being picked up and dropped off. And for Leo, he has a doctor examination in the tomorrow, so he wants to return to his home to prepare for the examination. So he wants to travel from Hunter Association to home, and his expected time window for pickup and drop off is shown in the table. And the Hunter Association have designed a flying boat to fulfill their transportation request, which the physical location for those friends are shown in the slide. So one possible way might be first the flying boat go to pick up Killua and Gon at Kukulu Mountain, because it has they have the tightest time window for being picked up. So go first to pick those 2 boys at Kukulu Mountain, then go to pick up Leo at Hunter Association, then send Killua and Gon to Sky Arena, which is their destination, then go to pick up Kurapika at Tokyo and send Kurapika at New York. And then finally, Leo has finally returned to his home. So during this procedure, you may observe that Leo is not very friendly to this plan, because he is the last person to be dropped off, and he shares a long ride with his other friends, and he is the last one to be dropped off. So he has a very long user ride time at the flying boat. How about another plan? Maybe first we still pick up Killua and Gon at Kukulu Mountain, then Leo, then Kurapika, then we send Kurapika to New York, then we send Leo to his home, and finally we drop off Killua and Gon. But this might be a plan that will violate the time window, because Killua and Gon, they have a relatively early time window for being dropped off, but they are the last one to be dropped off. So this could not be a possible one for those 2 boys. So how about we don't have a flying boat, this very efficient traveling mode? We only have our electric cars, which we need to consider the recharging operations during this trip. How about that? How about if we have many cars and have hundreds of customer requests to be fulfilled? How to arrange those cars to serve those customer requests with respect to a lot of constraints? And this is what we will tackle during the presentation. So this is the plan for my presentation, and I will first introduce the electric autonomous diorite problem. And a series of transport related problems such as greenhouse gas emission and congestion have appeared, as Flo and Jacob have presented in the morning. And 2 possible directions have been proposed to address those concerns. One is to use battery electric vehicles. Another is to provide ride-sharing services. And dial ride problem, as I presented to you in the small story before. So dial ride problem is defined as to design the minimal cost route plan for a fleet of vehicles to serve customer requests that specify their origins, destinations, and time windows. And however, the research gap is that few studies have been done to investigate the influence of electric vehicles on the dial ride problem. Most of the study considered conventional vehicles, which don't need to consider the operation of recharge on the route. Few studies have been investigated the influence of electric vehicles. And the only one, to the best of my knowledge, is by Bongiovanni, which has proposed an exact method to tackle the electric dial ride problem. And those authors have proposed a branch and cut methods that can solve incidents with up to 5 vehicles and 14 requests optimally. And here is a solution example for the electric autonomous dial ride problem. And in this figure, different colors represent different vehicles. So you may observe from this figure that each vehicle starts from an original depot and serve a set of customer requests and then return to the final depot. And when the vehicles are running out of their energy, so it's necessary for those vehicles to visit the recharging station during their trips, during their services. And so here you can see the recharging station is visited before visiting the next customers, and we need to include this aspect into our study. And before I talked about the electric autonomous dial ride problem, I would like to first precise what is the characteristic for typical dial ride problem that are different from the vehicle routing problem. I suppose that you have known what is vehicle routing problem because we have a lot every day. So what is the characteristics of dial ride problem? First, as I have illustrated, we need to consider the pickup and drop off of the passenger requests. So it's associated to two kind of constraints. That is, we need to consider the drop off node should be visited after the pickup node. And the two nodes for one request should be served by the same vehicle, not by different vehicles. And the second characteristics, which is the most important one, is that we need to consider the service quality. As I illustrated in the small story, Leo is the last one to be sent to his home, and he spent a super long time at the flying boat. So it's not very friendly for him, of course. So we need to maintain a certain level of service quality while serving the customers. And this is often realized by setting a maximum user ride time in the constraint part to maintain a certain level of service quality. And this point will introduce another point, that is, the delay of service begin time. Maybe it's helpful to eliminate some unnecessary waiting time and to improve the service quality. I will precise this point by giving you a small example here. Here is a partial route. The vehicle travels from the depot and then to the first node for the first passenger 1+. I assume that each request only associated to one passenger. So the passenger 1 is picked up at 1+. Then vehicle comes to pick up passenger 2 at 2+, then drop off passenger 1 at node 1-, and then drop off passenger 2 and 2-. And here is a feasible schedule for vehicle to serve those customers, which precise the service begin time at each node. And we observe that actually the vehicle arrives too early at the node 1-, because the time window for 1- starts at 155, while vehicle arrives 10 minutes before the 155. Unfortunately, there are 2 passengers on board, so the 2 passengers will wait 10 minutes, both waiting 10 minutes as a vehicle. So in total, 20 minutes waiting time have been generated in this case. However, we can improve the schedule by delaying the service begin time as a node 2+, from 130 to 140, so that passenger 2 he or she doesn't need to wait at the node one minus. So the total user write time is decreased from 105 to 95. We are saving 10 minutes of waiting time. We are improving our solution by delaying some at some nodes the service peak. So usually this the solution is the schedule is often being improved by using the 8-step method proposed in the work of Bordeaux and Laborde. It can improve the solution's feasibility. However, it's just to improve. There is no guarantee to obtain the optimal schedule with the minimal excess user runtime. No guarantee for that. It's just to improve. However, in our study, the electric autonomous dial-write problem, including the maximal user write time as a constraint, we consider also a weighted sum objective function value, which including two objectives. One is the total travel time for all the vehicles. Another objective is the total excess user write time for all the users. So we need to optimize the schedule rather than just to improve the feasibility of the schedule. To have a better schedule is not enough. And no method have been designed yet to determine the optimal schedule that has the minimal excess user write time. So another characteristic is of course the use of electric autonomous vehicles in our network. It will introduce, of course, the detour to recharging station on the route, and we have considered a partial recharging at the recharging station. So here is a trade-off because of the partial recharging. Of course, if the vehicle recharges for a long time, it will visit more nodes after the recharging. Of course, it will extend the driving range. However, the longer recharging time might be conflict with the time window constraint for the succeeding nodes. If there are nodes that has a very strict time window constraint and you recharge for a long time at the recharging station, you might not be able to serve it. So this is a trade-off we need to consider. So we need to tackle this very carefully. And as we considered autonomous vehicle, so no drivers are related to each vehicle. So theoretically, the vehicle can be mannered in a non-stop way. Yeah, there's no restriction on the road duration, and there is a limit of visit to each recharging station. And finally, we have a more specific and artificial constraint in the model, that is the minimal battery level at the end of the route. Why we consider these constraints? Because if we don't consider that, the vehicle can serve as approximately 20 nodes without visiting any recharging station. This means most of our benchmark instance can be solved without visiting any of the recharging station, which is not our interest, because we want to evaluate our performance, the algorithm performance. Well, it has a need to visit the recharging station. We want to analyze their behavior. So we have considered 3 different scenarios as which represented by a ratio of minimal battery level at the end of the route. That means three different scenarios: 10%, 14%, and 17% of the total energy being kept at the end of the route. With the increasing value of this percentage, it means vehicle should keep more and more energy at the end of the route while returning to the depot. That means it's necessary for those vehicles to visit the recharging station before returning to the depot. And it will allow us to analyze the routing results according to those 3 different scenarios: low energy restriction, medium energy restriction, and high energy restriction. And here is the objective function for the weighted sum formulation. And this is the decision variables. And for the constraints, here is listed here. And we are tackling actually with the static version of dial-write problem. So all the requests we are known in advance. We are knowing all the requests in advance. The dynamic version that I will tackle in the future in my thesis is that the request can be updated during the day, and the vehicle has the right to reject or accept the new request generated by the customers. But now in our study, this study, we're tackling with the static one. So all the requests are known in advance. And we have formulated the electric autonomous diorite problem into a set covering problem, which is also called master problem. And the set covering problem, we have the decision variable is called y omega. It's a binary decision variable, and the big omega here is denote the set of all feasible routes. So with the increasing number of customer requests, this will grow exponentially. So it's impossible to solve directly this version, and we have converted to a relaxed version of the master problem, which is a continuous restricted master problem, a subset of omega. And we use the method of column generation to add columns to omega prime, the subset of omega, and solve again the continuous restricted master problem. And I will precise the methodology in the next slide.
Maybe quickly, if you can, to leave room for questions. Maybe if you wrap up in a few minutes.
Okay. So we have proposed a column generation to solve this problem, and the continuous restricted master problem is shown in the left-hand side, and the pricing subproblem is formulated with the dual variables associated to each of the constraints in the continuous RMP, and the objective function, and the pricing subproblem need to satisfy a series of constraints. And the column generation is described as an iteratively solving of continuous RMP and the pricing subproblem. The continuous RMP will update with the pricing subproblem the renewed dual variables to formulate the objective functions. And the pricing subproblem is to find the negative reduce the cost columns and add it to the omega prime. And this problem will be solved again to update the dual variables associated to each constraint. And this will be iteratively solving until no negative columns can be found. And we have proposed a labeling algorithm to solve the subproblem, because actually the efficiency of solving subproblem is the key factor that impacts the overall algorithm performance. And the labeling algorithm, the general idea of the labeling algorithm is that we extend the partial path from the original depot until the destination depot, node by node. So for example, we send node by node, and on each node, a label is associated with each node. And in each label, there are several resource attributes included in each label. And while extending the label and the partial path, we need to check the feasibility for the extension to make sure that each extension is feasible until we reach the final depot. And we return all the routes with negative reduced cost. And during this extension procedure, the resource extension function is used to update the level of the new node. And we can use a dominance rule to accelerate this algorithm. For example, here there are three partial routes. Both of those three partial routes end at the node I. If the partial routes red one dominates the two one, so we don't need to consider those two. We only need to extend this one, because if this one is better than the two, you can replace this plan. And so we only need to consider the red partial route. And now I will quickly summarize the computational results. We have examined our algorithm on 3 instance sets, and the first 2 instance sets are based on the study of Bongiovanni in 2019, which is initially introduced by Bongiovanni. The first one is based on the it's based on typical diorite problem, but supplemented with the character of recharging station. And the second one is based on the real-world ride-sharing dataset of Uber technology. And the maximal instances contains in the 2 benchmark set is up to 5 vehicles and 15 requests. And we have constructed ourselves a larger instance set with up to 8 vehicles and 96 requests, which is called type R instance. The first one is type A, the second one is type U, and the last one is type R. And for each instance, we have tested 10%, 14%, 17%, those 3 scenarios on each of the data set. And here is the results for type A instances under 10% of the energy being kept at the end of the route. And here are the results. And we summarize with our column generation algorithm, we can solve 12 out of 14 instances as a root node without branching, without calling any branching. And we improve the lower bound that's reported by Bongiovanni by 0.7%. Because in this case, actually most of the instances solved optimally also by Bongiovanni. So their lower bound equal to the objective value. There is actually no space for improvement of the lower bound. But for those instances that doesn't prove optimality in the work of Bongiovanni, we can improve the lower bound of those instances by up to 5%. And the computational time has decreased a lot. And here is the result for 14% case, where we also solved most of the instances optimally as a root node, and we have reported 4 new optimal solutions identified. But here we find an exceptional occasion, because we found actually we prove optimality for this instance. The optimal value is 347, while the optimal value reported by Bongiovanni is 348, which is not equal and except the tolerance gap. And we actually find there a wrong parameter using in their study, which they actually cut off some optimal values for some instances, and our approach finds the real optimal value for those instances. And just something to implement. And for the most difficult cases, with our column generation, we are able to solve 5 out of 40 instances optimally as a root node, and we report 7 new best solutions, and we've improved the lower bound and also with the lower computational time. And here is for user instances, similar findings have been observed, and our algorithm can tackle the large instance set, while the literature method cannot. This is a new result reported by our algorithm. And here is some summary for the performance of the algorithm. And I will move directly into the conclusion. So we have proposed an efficient algorithm to tackle the EA-DARP, and we have proved a significant improvement on the lower bound quality and the solution quality. And the column generation algorithm is able to handle a larger scale instances. And the future work will consist first, extend our labeling column generation to the related topics such as electric pickup and delivery problem with time window. And also another context is to consider a multiple objective optimization. And another interesting direction, maybe we can consider a dynamic version of diorite problem, because we are now tackling with the static one, and we can consider to handle the dynamic one with the request can be added, renewed. So here is a reference. Thanks for your attention.